Okay, so let's get started. I want to begin by thanking my collaborators. So first and foremost, I'd like to thank Katie Morrison, who has really worked on me for all of this work that I'm going to, almost all of it, that I'm going to show you today. She's a professor at the University of Northern Colorado and just a long-term collaborator of mine. Caitlin Parmalee is a former graduate student, Chris Langdon and Jesse Genison were former postdocs in the lab. Nikki Sanderson, who's here, is a current postdoc in my group. And then Josh, Juliana, and Caitlin are current grad students who have also worked a lot on this work. And you'll see some work of Juliana's, especially towards the end. And I'd also like to thank Vladimir Itzkov and Anna Degeratu, who did a lot of work in some of the precursors to what I'm going to talk about today. And finally, my WinComp group, who I probably will run out of time to get to the nerve theorem stuff that we did together, but just in case, I'd like to thank them always anyway. Okay, so let's get started. The starting point, sort of conceptually, for what I'm going to talk about really goes back to the 80s with the work on the Hopfield model and Hopfield networks. So this should be familiar to most people who study mathematical or theoretical neuroscience, and many neuroscientists more widely, of course. And the basic idea in these models is that you're going to model memory patterns or stored patterns of activity in a network as fixed point attractors of the dynamics. And this really, kicked off this idea of attractor neural networks. So these ideas were around before, but the Hopfield model really made them popular and brought a lot of physicists into neuroscience to study questions such as, how many attractors can you store in a network, capacity questions, and various aspects of how neurons can compute using this kind of framework, right? So this is very much the framework of a recurrent neural network that has attractors. And in my work, we are focused on not the Hopfield model, but sort of I think of a more modern version of it, threshold linear networks. And these are really a firing rate model. So again, you have neurons, and they're interacting according to recurrent connections. So there's a W matrix that is capturing the strength of the connectivity. And the dynamics of the neurons really are evolving according to the so-called threshold linear dynamics. So there's a leak term. In the absence of recurrent inputs, a neuron will just decay to rest or to a zero firing state. And then the recurrent inputs are captured by this sum of the Wij, Xj. And there's a combination of threshold and external input that's captured by the Bi. And so we're going to refer to this, the data that kind of specifies a particular threshold linear network is really the pair, the matrix W and this vector B, okay? And just this notation, the brackets plus, is denoting the threshold nonlinearity. So it's a maximum between 0 and the argument of the function, okay? So the machine learning people like to call that ReLU, or the rectified linear unit. So perhaps remarkably, these networks can display the full repertoire of nonlinear dynamics, even though you may notice already, if you think about the equations a little bit, locally, these are linear systems of ODEs. So what's happening here is I have a piecewise linear system of ODEs. So the equations inside this nonlinearity can be thought of when you set that to 0, which is when you switch from one side to the other of the nonlinearity. That defines a hyperplane in the state space. And each one of these equations has its own hyperplane with the normal vector given by the row of the W matrix and a shift given by the B sub I term. And this hyperplane arrangement chops up the space so that locally you have honest-to-goodness linear system of ODEs because you've picked one side or the other of the nonlinearity in each chamber. But despite that, it's in the trajectories passing between different chambers that you see all the nonlinear behavior emerge. Okay, and this can arise even for effectively inhibitory W matrix. So, 20 years ago, I would say the kind of mathematical study of these networks really kicked off with some beautiful work by Hanlesser, Sung, and others at MIT at the time on the symmetric case. So they were studying threshold linear networks where the W matrix is symmetric. And in that case, you can prove a result very similar to the classic Hopfield result, where you can guarantee convergence to one of multiple stable fixed points. And with Anda and Vladimir, we followed up on this and continued working on the symmetric case for a while. So we wrote some I think, interesting papers about the collections of fixed points that you can have and what kind of neural code you can encode. Then I started working with Katie, following up on that. But really, we wanted to get away from the symmetric case. So we started there because that was in some sense simpler to tackle. But today, I really want to talk about both. I really want to talk about non-symmetric W matrices. And the focus now is not just on stable fixed points and fixed point attractors, but on stable and unstable fixed points, and because that enables us to look at dynamic attractors. Okay, so this is just kind of a dump of references that where you can find things that I'm talking about today, but I want to sort of get straight into the motivating question, which is, what is the relationship between the attractors of a network and its recurrent network architecture? And the focus is really on the pattern of connectivity as reflected in a directed graph. Okay, so we really want to answer the question, suppose you're given the structure of the network, suppose you're given a directed graph that captures that structure, what can you say about the attractors? And I want to make this very clear. We care not just about stable fixed point attractors, but also dynamic attractors, limit cycles, quasi-periodic attractors, and so on. And we want to be able to read that off of the structure of the graph. And that requires us to look at both stable and unstable fixed points. So let me give you an example of the kind of rich dynamics that you see in these networks. So here's a network with just 9 nodes. So I've shown you the graph of it. This graph is giving me a W matrix, which I'm not yet showing you, but let's just say from this graph I get a W matrix, and then I can evolve the network according to the TLN dynamics. So remember, these are just the dynamics that I showed on the previous slide. Okay, so there's a W matrix coming from that graph, and now we really want to focus on the effect of the local connectivity on the dynamics and not think of the dynamics as being reflecting a changing external input. So we're setting the external input parameter, the B, it's constant, okay? So every neuron is getting exactly the same, external drive. And so the different dynamics that you see here are truly an emergent property of the recurrent network, and they're not driven by changing dynamics outside. And so what we see is that depending on initial conditions, very, very different things can happen for the same network. So here I'm showing 4 different solutions, all coming from exactly the same equations, exactly the same W matrix. The only change is the initial conditions. So when I initialize on some nodes, so for instance, if I initialize in over here, the bottom left, you can see my cursor, right? This is, I'm falling into a stable fixed point where a pair of nodes 4 and 8 are firing. A different initial condition takes me to a different stable fixed point where 1, 8, and 9 are firing. Note that there can be overlap between the neurons that are involved in these different attractors. So these are the classic Hopfield style stable fixed point attractors. But now when I go on to some other initial conditions, I can fall into a limit cycle or even a strange or chaotic attractor, okay? Again, for different initial conditions. And all of these attractors, the remarkable thing about these networks is that all of these attractors are in some sense predictable from the structure of the graph, okay? So how do we get to the W matrix from the graph? So we consider a special case of threshold linear networks. In order to really focus in on the graph structure, we consider a special case where the graph is fully determining the W matrix. And, but we are staying within the realm of inhibition-dominated networks. And so what we imagine is that we have a network of excitatory neurons in a sea of inhibition. So there's some strong inhibitory background network, or a global inhibition, if you will, that is causing pairs of neurons to effectively inhibit each other even when there's an excitatory connection between them. So you think of the total interaction as being a sum of excitation on top of this strong C of inhibition. And this yields to two values for the interaction strength. So there's a value -1 plus epsilon. Epsilon need not be small, by the way, but we just chose epsilon and delta as our two parameters because we had used other Greek letters, too many other Greek letters for other things. And this is a value above -1. The -1 minus delta is a value below -1. Where does the -1 come from? The -1 is the self-interaction term, and it is the strength of the self-inhibition in the absence of recurrent inputs that are superthreshold, okay? And I should note as well that there's an implicit time scale here for the leak that has been set to 1. And so it's not that there's something special about 1, really the -1 is in units of this time scale that we've set to 1. And so what we're really looking at here with these W's is when there's an edge in the graph from I to J, or from J to I, then Wij is bigger than -1 because that means that J inhibits I less than it inhibits itself through its own self-leak term. When there's not an edge, the inhibition is stronger, so more negative than the -1. And so you really should think about the graph as encoding the pattern of weak and strong inhibition. Okay, when there's an edge, it's a weaker inhibition. When there's not an edge, there's the strong, just the background strong inhibition. And weak versus strong is determined with the reference point, which is the self-inhibition from the leak term. And so we think of these as generalized winner-take-all networks, but you can just think of it as a special case of TLN dynamics. So if we wanted to sample different networks and try to look for interesting rich structure, instead of just taking random matrices, random W matrices where we're perturbing around some point, this allows us to use these graphs to find kind of faraway points in the parameter space where interesting differences in the dynamics arise, and to connect those directly to the structure of the graph. Okay, so I'll try to speed up a little bit now, because I want to get to a cool application at the end. But one of the things you can notice right away with these networks is that you really can tackle the different emergent dynamics fully as sort of purely as a function of the structure, of the global structure of the graph. So I'll just quickly say, here we have 4 different networks. This is a kind of a simple example to show the idea that the local degree sequence is not enough to sort of determine the dynamics in these networks. So all 4 of these networks are degree matched. That means that if I look at the in degree and out degree associated to each node, so for instance, node 1 in graph A here has in degree 1 and out degree 2. So I give it a 1, 2. I do that for all the nodes, I get the degree sequence. And I do that for every graph, and every graph has its own degree sequence. And I sort it in some canonical way. All of these graphs are identical as far as their degree sequence. They're also identical, the networks that I've made from these graphs are identical as far as the epsilon and delta choice. Okay, and so everything locally is the same for all of these networks. The only difference is the actual structure of the graph. Okay, and so if we see different dynamics here, right, we can truly say this is emergent from the connectivity structure. It's not due to changing external inputs. It's not due to anything other than changes in the connectivity structure. And there are wildly different dynamics, okay, in these degree matched graphs. The first one has a global attractor, a single limit cycle that always emerges no matter what the initial condition is, okay? And it corresponds to a 3 cycle in the graph, 2, 3, 5. And you can see that actually in the limit cycle, the activity follows the arrows of the graph, okay? In the second case, we get 2 limit cycles. In the third case, we get 3 stable fixed points. In the fourth case, we get 4 chaotic attractors. So all of these are quite different. But of course, we've seen in the previous example that you can also have these different kinds of attractors coexist in the same network, okay? We also get some very interesting dynamics in highly symmetric cases. So here I have what we call the 5-star graph. So it's a tournament, and it has a cyclic symmetry. There's a boring, I call this a boring attractor that's associated to it. It's a limit cycle where the neurons are where the activity is following the edges along the outside of the graph. So 1 to 2 to 3 to 4 to 5 and so on. And you can see the rate curves are color coded according to the neurons. So these are the curves xi of t for each of these neurons. Now, the exact same network, exact same W matrix, different initial condition. All I'm changing is the initial condition can now fall into this completely different attractor, which I call the Gaudí attractor because it reminds me of the architect in Barcelona. And I've never, prior to this, I'd never seen anything like it. The curves look like they're melting, okay? But this really is an attractor of the network, and it's very stable and reproducible. And it corresponds to to a different cycle in the graph, 1 to 3 to 5 to 2 to 4 to 1. Okay, so you're seeing, now let me just take a moment to remind you, these are effectively inhibitory networks. Every neuron is actually inhibiting every other neuron. Okay, so it's not like we're flowing along edges of the graph. The edges of the graph are indicating weak inhibition. The non-edges are indicating strong inhibition. But it's not too bad of an idea to think of flow along the edges because in fact that's what happens, right, when we look at the dynamics. So that's what makes this sort of a nice graph. And then here, let me just show you an example in case for those of you who know about quasi-periodic attractors. For this other graph, we also see two different two different dynamic attractors emerge. The first is a limit cycle, kind of the boring one, going along the outside. And the second is a quasi-periodic attractor. And what you see here is a projection of this beautiful torus that's traced out in the 7-dimensional state space. And we've just taken a random projection so that you can see the torus structure. Okay, so how do we analyze these things mathematically? We look for the fixed points, okay? So obviously, fixed point attractor, the stable fixed points correspond to attractors. They are their own attractor. But it turns out that the unstable fixed points are also extremely useful for figuring out dynamic attractors, okay, in these networks. And the way we study the fixed points is really by thinking of this geometric picture of the threshold linear networks as this patchwork of linear systems. So I said a little bit about this in the beginning. And let me say it again. You can think of your n equations, right, as having, as defining a hyperplane arrangement. So the argument inside the nonlinearity, we refer to this like y1 through yn, and setting yi equals 0 defines a hyperplane in my n-dimensional state space. And so I have n hyperplanes, one for each equation. And once I'm inside one of the chambers of this hyperplane arrangement, I have picked one side or the other of the nonlinearity. So either I can drop the brackets because I'm on the plus side, or I set it to 0 if I'm on the minus side. And now I have an honest-to-goodness linear system of ODEs inside that chamber, right? So you have all these different linear systems. They're related to each other because they're all coming from the same W matrix, but locally the system is linear. And there are some nice things you can unpack from that. In particular, there's a one-to-one correspondence between the fixed points of the full TLN and allowed supports of fixed points. So it turns out that in order to have a fixed point of the full network, what you need is to have a fixed point of one of those linear systems that actually lies inside the correct chamber where that linear system is governing the dynamics. Right? Every one of these linear systems is, we have a non-degeneracy condition actually that we require for our W matrix. So every one of those linear systems has a single fixed point associated to it, but that fixed point may or may not reside inside the chamber where the linear system is governing the dynamics. Okay, and only if it does is it a fixed point of the entire system. And so the whole game is to figure out, okay, which chambers contain their own fixed points. And so you can really label the fixed points by their supports, which are subsets of the neurons 1 through n. And that is the game. And so this FP of W or FP of G, when we think of a particular graph with epsilon and delta parameters, is telling me all the allowed supports. And so you can, here's a very simple case with a 3-cycle. You see this nice limit cycle attractor that we get. Here's the hyperplane arrangement with the different yi's equal 0. There are 8 chambers that you're chopped into. And the limit cycle necessarily has to cut across more than one chamber. It cannot reside inside a single one because that's a linear system. Linear systems don't have limit cycles. And so the limit cycle is actually emerging as a trajectory that spirals out from that central chamber and then cuts across different chambers, but like comes back to the central chamber and catches the spiral at an earlier point. So it's always spiraling out when it's in the main one. And then this patches together to give a perfect limit cycle. Okay, so, all right. So hopefully I've convinced you at this point that we care about the fixed points and that there's a combinatorial flavor to them and that we can think of them nicely and productively in terms of this hyperplane arrangement, in terms of this geometric picture. So now I just want to say very quickly that from these insights, we're able to develop a theory of graph rules where we can actually analyze the structure of the graph and know something about the fixed points, right? So we can prove theorems that say if the graph has this structure, there's going to be a fixed point with this support. Or if the graph has this other structure, there will not be a fixed point with this support. Okay, so the graph rules are ways of looking at the combinatorial data in the graph and predicting fixed points or predicting absence of fixed points. And so I will just show you one of them, one of the simple ones, which is the uniform in degree graph rule. And that one tells you that if you have a subgraph that is uniform in degree, which means that every node is receiving the same number of incoming edges. So up here are some examples. They need not all be symmetric. So for instance, graph A4 is uniform in degree 1. Every node gets only one input. These graphs are special in the following sense. So if you have in your larger network an induced subgraph that is uniform in degree, then you're guaranteed that the nodes in that subgraph support a fixed point, meaning there is a fixed point where only those nodes are firing and all the other ones are silent, if and only if there's no node outside of the subgraph that receives d plus 1 or more edges from the nodes inside. So sigma is the collection of nodes inside. And d is the degree, the uniform in degree. So from this theorem, I can already answer sort of a question you might have had earlier when you looked at this example. We have this nice limit cycle corresponding to the 2, 3, 5 3-cycle in the graph, but there's another 3-cycle in the graph, 1, 4, 5, and there's no corresponding limit cycle for that one. What's different? What's different is that one of them has a surviving fixed point, the other one does not. So there's an unstable fixed point associated to 2, 3, 5, okay, which is kind of at the heart of this dynamic attractor of the limit cycle. It kind of goes around it. But 1, 4, 5, there is this external node 2 that receives too many edges from it, and that kills the fixed point. So the graph rule is telling me which of these subgraphs is going to keep its fixed point when embedded into the larger network. And the ones that keep their fixed point are the ones that carry their attractors with them. So that is the heuristic that we use. So we can prove things about the fixed points, and then we have a heuristic that tells us how to connect certain unstable fixed points to predictions about dynamic attractors. Okay, so we have many of these graph rules, and I don't have time to get into it. Now I just want to, I have 5 minutes left maybe? Okay, because I started late. Now I want to show you an application, okay? So, to make a long story short, we've been able to prove a variety of rules like this. And in fact, we're even now working on sort of axiomatizing them in the following sense. So we have many, many graph rules, but we can strip down to some elementary ones. So I'll just show them. There's some elementary graph rules that we prove directly from the TLN equations, and then sort of derived graph rules that we can get once we know that these are true. Okay, so we're trying to really systematize the graph rules and figure out like what's sort of the essential ones from which we can prove subsequent ones. And now I want to tell you about one of the more complicated graph rules that stems from the elementary ones, but that leads to this nice application. And that is graph rules about simply embedded graphs. And in particular, as a particular application, we have this concept of the cyclic union. So if you take a bunch of graphs and connect them together in a way where the nodes from one of them will all have forward edges onto the nodes from the next one in a cyclic manner. So tau 1 through tau n are the collections of nodes corresponding to graphs 1 through n, and now I collect them in the cyclic union. Then it turns out that I can prove a graph, well, we've proven a graph rule that tells us the fixed points of the large composite network from the fixed points of the individual ones, okay? And what it says is that precisely that the fixed points of the larger network emerge by gluing together supports for fixed points from the individual subnetworks, okay? If you think about the hyperplane arrangement picture, it's kind of crazy because you have these hyperplane arrangements for the individual subnetworks. Now you sort of glue them together into this giant hyperplane arrangement. And now I'm telling you that the fixed points of the large one are completely determined and predicted in a very simple way by knowing the fixed points from the smaller networks and just gluing them together in all the different configurations, okay? So, so this is a nice rule, and there are many related rules like that follow from some of these elementary graph rules. The gluing idea, I think, is very nice, and for those of you who know a little bit of topology, you almost have like this pre-sheaf structure where you think of the fixed points of the subgraphs as kind of sections of a sheaf, and then the gluing is sort of like a sheaf property that allows you to take the local sections and glue them together into fixed points of the whole network. So there's some nice structure there that I don't really have time to talk about, but I want to get now to the application. So using the cyclic unions graph rule, which Katie and I developed in collaboration with my former grad student, Caitlin Parmalee, we are able to engineer some very nice networks with prescribed attractors. And this is work of my current grad student, Juliana Londono Alvarez. And she was able to tackle this question of having simultaneous limit cycles encoded in the same network to reflect different quadruped gates. Okay, so this is kind of an old problem in neuroscience of central pattern generator circuits. Is you have animals that can support different gaits in their locomotion. So the classic example is you have a horse. It can walk. It can trot. Gallop, pace. Etc. It has these different gaits. Pronk is actually not one that the horse can do, but we can put it in the same network. So we just, it's like a super animal that we've designed this for. And if you look in the literature, even very recent literature, like this Nature Communications paper from 2019, most of like all of the models really require parameter changes to go from one gate to another. Okay, so they posit synaptic plasticity or some kind of gating variable has to change or some kind of parameter change to the model in order to transition from, say, walking to trotting, okay? And we wanted, using the machinery of our threshold linear networks and using our graph rules, we wanted to see, can we make a network where all of those limit cycles for the different gates coexist without having to change parameters. That it's just a matter of initial conditions, whether you fall into one gate or the other. Okay, so in principle, it's very difficult to do because you have these different limit cycles that have the feet, the same neurons that control the leg motion, going in different patterns, and you want to create a circuit that allows for all the different patterns without changing any parameter, truly coexistence of those patterns of activity, just from it and accessing one or the other just based on changes of initial condition. So Juliana set to work, and using the cyclic union idea, she was able to make circuits, okay, for different gates. So first she did one at a time. So here's her circuit for the bound gate. Here's her circuit for pace. So the pattern of the feet hitting the ground or the hooves hitting the ground is different in each case, but she's got to be reusing the same neurons, the left front, left back, right back. Okay, so these colored ones are the different neurons that are controlling the legs. Then she did trot. That one's different because they have to hit in a very different pattern. Walk. And pronk. Pronk is a very cute one where they're all up at once and then come back down. The horses don't really do that, but we wanted our model to sort of do even more, okay? And so for each of these, using the cyclic union idea, she's able to get them to have the right pattern of activity. So you can see these graphs at the bottom. I'm showing the pattern of activity. You can see it emerges in the network, okay? So she gets it to work. And then here's the miracle. How do you make a network that has all of them? We glued these together. We literally just took the union of the edges in all of these graphs, okay? And just, identified the nodes that were for the same feet and glued it all together and made a super graph, okay? And now the question is, do we have any chance of preserving those attractors that she carefully designed, for these subnetworks? And so this is the super network. It has 24 nodes. There's the same 4 that are, many edges coming in and out of them. It looks very complicated, but it's really just a gluing of those simple networks that she had, one for every gate. And this is the adjacency matrix. And now I just want to stress for you, this is again in the framework of the combinatorial threshold linear networks. The only data specifying this network is this adjacency matrix, the epsilon and the delta, and that tells you what the W entries are. So that gives you the full W matrix, and then theta is set to 1, okay? So all the information to make this network is really here on this slide, okay? If you can read all the edges off of that graph. It's a little bit of a messy picture, okay? And lo and behold, from the super network, we see all of the individual limit cycles. They are all preserved when we glued it together, okay? That actually we did not have theory to guarantee that would happen, right? But it's just these different solutions are kept so well separated, right? Somehow the network is able to maintain them all. And this means, by the way, that because they're all there, they're all stored in the network, you can go from one gate to another by a simple kick. So here is now a simulation with one initial condition, and we started in the bound gate. And then after a while, we kick neuron 15, which is one of the neurons involved in the pace gate. It's not one of the 4 legs. It's one of the neurons involved in, one of those cyclic unions, but not in the bound one. We kick that neuron. That just means we make the theta value for that neuron go high for a little bit and then come back down. So then we're back to exactly the same network in this period. And now we're in pace. And then we kick another neuron and we transition to walk, and another neuron and we transition to prunk, and another neuron and we transition to trot. And so you can see here, because these all coexist in the same network, we don't need any change of parameters. Nothing has to change about the network. All you have to do is kick a neuron to sort of take you to another part of the, another basin of attraction, and then you fall into the other gate. And it's very, very simple, right? So if you, had to design animals, right, and how they would then locomotion for them, this would be a very elegant solution, right? You don't need to have synaptic plasticity or any strange changes to the network. You just naturally transition from one gate to another. Okay, now I think I am finally out of time. We added noise to test for robustness. So I just flash, this slide about the noise. If we add 1% noise to the W matrix, we still see the perfect transitions. If we kick up the noise, we see some transitions fail, but maybe we just have to stimulate more strongly and so on. And so there's a lot of tests we can do for how robust this is. But these limit cycles really are, they're coexisting in the same network. Okay, and I think I will end there. This is the last bit with the Wincomp group, the nerve theorems, where we use this. We can cover our large networks by these directional graphs that are special. And this allows us to reduce to the nerve of the network and have a subgraph that is simpler. And so we've been able to prove some nice theorems connecting the fixed points of the large network to the fixed points of this reduced graph. It's like a dimensional reduction technique, but with an eye towards the fixed points. And that also allows us to predict dynamics and so on. So I will end here. My conclusions. First of all the fixed points matter. By paying attention to both the stable and the unstable fixed points, we're able to get a handle on dynamic attractors. The graph structure of the TLN is heavily constraining the allowable dynamics. So this really is a model where you have a chance. It's surprisingly tractable. You can analyze the graph and make predictions about the dynamics, and then run the simulation, and it works. And then I talked about this application with the CPGs. So just want to thank again my collaborators And then maybe I'll end with this slide. We are having a semester-long program in a couple of years at ICERM, which is one of the math and computation institutes at Brown University in the US, so it's NSF funded. And we recently got approval to run a full semester-long program. Actually, one of the co-organizers is Catherine Hess, who's talking next. And this is going to be a mix of people with backgrounds in mathematics, in particular applied topology, and theoretical neuroscientists. And so the goal of the program is to really bring mathematicians and theoretical neuroscientists together to work on developing mathematics that will push the fields forward. So if you're interested, shoot me an email, or you can Google this and find the program. But we are now starting to put together the workshops, invite people, and so on. And we would love to have people in this group apply or show interest, and we can invite you and so on. So please. Anyway, just advertising. It's so awkward to advertise stuff, but there it is. Okay, I'll end there. Thank you so much.
Any questions from the in-person audience? Patricia.
Thank you for this very nice talk. I'm not a specialist of dynamical systems. So at one point you said, so you're sure you created a graph that has all the fixed points that you wanted. Mm-hmm. And then you said you still have to check that all the rhythms coexist. Why is it not sure once you have the theoretical?
Oh, so the theoretical results do not tell us. We have heuristics, we have, patterns that we see to guess the dynamic attractors, but just knowing the fixed points does not guarantee for us what the dynamic attractors are going to be.
Okay.
Yeah, so the limits, even the existence of these limit cycles is hard to prove, right? Okay. And so, but we know they're tightly connected. So it's like, because of that heuristic, right, then once we prove things about the fixed points, we're like, oh, we believe now. And then it's like more of a theory in the science sense, right? Okay. Where it's like, we can predict them, but we still have to run the simulations to see that it actually works. Mm-hmm.
And also I had a more maybe philosophical question. Mm-hmm. You said that this could be seen as linked to artificial neural networks because this is a ReLU function or whatever. You see? I
actually do not stress that, but.
Well, we could imagine a little bit. Uh-huh. And the way for the moment artificial network works, I think it's the fixed points that they are working on. Like you give an entry, you go until the end, it gives you this answer. And the way you're presenting it, it seems that you could encode much more with less neuron by also looking at all the rhythms that you can create with all of that. Mm-hmm. So what would you think about that?
Yeah. I mean,
no, but could you try to design something?
I think the classic deep learning networks, right? It's really implementing an input-output function. That's it. There's no dynamics. There's no rhythms. There's no oscillations. There's no magic.
Yeah, but there are more and more people, for instance, looking at spiking neural networks. Mm-hmm. that have the spiking neural networks. They have these temporal dynamics. Well, okay, they are spiking.
Yeah. No, that's why in neuroscience and theoretical neuroscience, we do care about all the dynamics, of course. I think in the machine learning, artificial intelligence, at least, I'm not an expert, there's lots of stuff going on. I mean, people do everything, right? But the main trends, like deep learning or whatever, really it's more, it's not focused on dynamics. It's more focused on, an input-output function that's going to classify or cluster your data. And that's, great. Lots of people are working on that. I think this is more fun. Because you get, but it's also just a different motivation, right? So here we're motivated by the fact that networks in the brain do more than just cluster, right? We do more than just look at images and decide is that a cat or a dog, right? They have to generate rhythms, oscillations. They have to generate patterns of locomotion. You have to be able to remember songs. There's it's not just kind of static patterns, right? Of course, the machine learning tasks also. We'll get there, and different groups are do think about that already, but yeah, we're much more motivated by the sort of networks in the brain. And if you look at networks in the brain, it's like they're constantly oscillating, they're constantly, generating all these rich patterns of activity. And so even simple, if you're going to model that, even with simple models like the ones that I present, you want to get at that richness of the dynamics. So.
Yeah, thanks for the wonderful talk. It was very, very interesting. Before I ask my question, let me just compliment on what you said on learning dynamics and machine learning and deep learning for dynamical systems. So it is true that there is a large bulk of work on, I'm too close to the speaker, I think, on classification, but you can also think about, trying to predict the next time step given your current step. And there's a very large bulk of literature on reservoir computing and recurrent neural networks, also from a neuroscience point of view, that also try to understand the structure of these networks and different types of fixed points and chaos you can get. So there is actually a very large bulk of work on this. So
and that stuff is close in spirit to what I'm doing.
Absolutely.
But that's coming from theoretical neuroscience community.
Yes. Okay, cool. So I was just wondering, because you showed this is really cool that you can get all of these different limit cycles, but in the actual behaving animal, it can spontaneously transition between these different behaviors. And not only that, there's a lot of variability within the same behavior. So it has actually been shown that in some cases, the dynamics is closer to chaos than it is to a limit cycle. The degree of fluctuations that happen within each of these so-called limit cycles is quite large. So I was wondering whether you could, comment on if it's possible to generate, this sort of variability and spontaneous transitions from a kind of intrinsic point of view in the construction of the network.
Yeah. So sorry. The examples I've been showing are, we're sort of very focused on, we want to model these particular patterns, right, and have them coexist and so on a network. Now, if you take, I didn't include the slide in the talk, but if you take, large networks of these, right, just make a very large graph, but still create the, a CTLN with the same kind of rule, you do see what appear to be spontaneous transitions and sort of large-scale chaotic dynamics. We don't understand it very well, like we don't have nice relationships between, these unstable fixed points are creating this, chaotic attractor or whatever. But just from playing with these networks, that does seem to be something that emerges very naturally. Unfortunately, I did not include those, but we have, many examples. But it is just at the level of examples now. So we don't have a good theory about it, but we do think that these networks are also supporting that. And in fact, when Hanlazer and Sung and company were studying them early on, they also, looked at those questions and viewed them as quite capable of producing the sort of edge of chaos kind of dynamics.
So in the pipeline, there is a question from Bruno Cessac, who can unmute himself from online, and then we have two questions from the audience here.
Hello, can you hear me?
Yes.
Yes, thank you. I have a question. Your hyperplanes somewhat define a partition of the fast space, and you could be tempted to use that to do symbolic coding, as it's done in ergodic theory and in classical dynamical system, hyperbolic dynamical system. The problem you have is your singularity set, where the dynamics is non-differentiable. I was asking myself, first, if you can write conditions so that the attractor does not sit on the singularity set, so you are away from it. And then I think you can find condition where on the Wij, where your system is either contracting or expanding, so it's uniformly hyperbolic. And I was thinking if you could use results from ergodic theory to characterize your dynamics. I was especially thinking of the shadowing lemma, which allows you to characterize periodic orbits and recurrent properties that could be helpful in your case.
Yeah, so I'm unfortunately I didn't hear all the details of the question,
sorry.
but I think sorry, the connection is not very good, and I'm in sort of an awkward position here. But I think one of the things you said is ergodic theory from classical dynamical systems theory, if that could be used to characterize the dynamics in some of these cases. Yeah. So I'm actually very fortunate to be a professor at Penn State, which is a university that our math department is actually a leader in ergodic theory and pure dynamical systems more generally. And so one of my graduate students, Josh Pike, is actually currently completely pursuing that direction. So he is like learning all the dynamical systems he can from people doing pure ergodic theory and trying to connect it. So So I guess the short answer is yes, we think that is possible, and we're working on it. So,
but my question was, how do you deal with the non-differentiability of your dynamical system?
Yeah, that's the tricky part.
Yeah.
Yeah. That's why we can't. I mean, so we talked to these people. I've talked to my colleagues before about this, and it's the system is not set up that you can just use a lot of the results out of the box, right? Yeah. Because it's just not quite right. You don't. There's some hypothesis always in a theorem that you don't satisfy, right? But there's something. Still, it should be adaptable, but it sort of requires more work, and so. I had to kind of wait until I had a graduate student who was really willing to do that. And so, check back in a couple of years, hopefully.
Thank you.
Yes,
Thank you.
by the time he defends, we'll have something.
Hey, thanks a lot for this presentation. I come more from neuroscience, so I have more related question because we are in biology used to very complex network, and here you show how you can, in a constructive way, have this multi-stability system. But can you reverse in some way the process? If I give you a very complex network, can you separate some underlying networks that are responsible for a given attractor or stable state?
Can we learn this from data for a complex network? That's the question. So so I think that is also kind of, I hate to say it, but that is also in the future work category for us. So we've been trying, because these networks are tractable enough, right? We actually can address the sort of forward problem. Right? You start with a network, you know everything about it. What is it going to do? Right? And that is hard as well. I mean, so people train networks, even if you go to machine learning, deep learning, people train the network. And then there's this question, okay, suppose someone handed you one of these trained networks, right? And didn't tell you ahead of time what they trained it to do. Could you look at the network and predict what's happening? It's hard, right? And so, So this, for us, these networks are an opportunity to really tackle the forward problem first, right? Which is what we've been doing for many years now. And the hope is that if you really understand the forward problem better, then you can do the backward problem, right? And so and in some sense, this engineering networks to do specific tasks is trying to do the backwards problem in sort of a simpler setting, right? Where we have, again, sort of control, like, okay, these are the different limit cycles we want. Let's engineer a network that does that. But that is sort of a reverse engineering question already. And then, so the longer term goal is that you can look at a data set, right? And apply, and develop some kind of learning rule where you would automatically train the network to reproduce those dynamics. That we do not know how to do yet.
Yeah, thank you very much for the talk. So it was very interesting to separate between initial conditions and structure to go from one fixed point to the other. I have a quick question, maybe it's not fun for you. Did you check for changing the weight to go from one fixed point to the other? So to have a dynamic kind of synaptic plasticity, but just having a rule to change the weight and...
Right, so I mean, and so, oh, sorry, these are other slides that I cut from my talk. So in this example, right, we added noise to the W matrix. So that just meant we added sort of random numbers, we just added a random matrix to the W matrix whose amplitude, where the amplitude of the individual entries was about 1%. And then we did a 5% and so on. So this is like randomly changing weights, just a little bit, right? We also have a completely different body, related, but that I haven't talked about at all today, body of work where we are trying to understand, for a given attractor, what weights can be freely changed while maintaining the attractor to be exactly the same. Okay, so this is another kind of cool thing about these networks that, and because this is a short talk today, I didn't get to talk about, but we actually can understand, using our theory with the unstable fixed points and so on, we're able to, at least in small cases, we're able to say, okay, here is a small network. It has this like motif in it that's responsible for some attractor. here are some weights where if I alter them, I'm going to screw up the attractor or change it or lose it. And here are other edges that I can freely move and preserve the attractor. And so part of it is understanding, like, in the space of W matrices, in the space of TLNs, we are mapping out actually directions that you can move and preserve an attractor. Even
and going from one attractor to the other?
And directions to go from one attractor to another, yeah. Okay. And so there's a whole, like, interesting bifurcation theory there. I don't know if that answers your question, but this is definitely something, that we're looking at. I just didn't get a chance to mention it. Mm-hmm.
Thank you, Carina, for this very nice and very dense talk. There was a lot of material. Mm-hmm. I have two questions. One is about cascades, and one is about bifurcations. Mm-hmm. So cascading, the idea of having this, multi-layers networks, mm-hmm. Can you actually, in some cases or every time, predict the dynamical behavior of the cascade of networks from your theory? I was under the impression that in some cases the answer was yes.
In some cases, yeah. It depends on what you. I mean, you're thinking of a network that has some kind of feed-forward structure, or yeah. So in fact, so there are different ways of defining the feed-forward structure. So we actually have this sort of, like, dynamic feed-forward structure that we define, and that's the last part of my talk I didn't get to. We're thinking about these directional graphs, and what makes a graph directional is that there's a subset of the nodes that supports all of the fixed points. Okay, so you have a large network, but then all the fixed points are supported on some subset. Okay, stable and unstable, right? And what we observe, and this is heuristic, is that the activity tends to collapse onto that subset. And then you string many of these together, you get like a cascading, and this is what we have with the directional graph. So this is sort of a cartoon example of that. And yes, we can say a lot in those cases.
I had a quickie. Mm-hmm. I was under the impression that your family of weights was a two-parameter family. You had epsilon and delta.
Yeah.
Have you thought of looking for bifurcations of your system of equations? 2 parameters is very small.
Yeah. Yes. Yes. We have. In fact, 2 parameters are very small.
It's non-differentiable, of course. It's piecewise linear.
It's piecewise linear, but yes. So the piecewise linear, so it's non-differentiable, so that's annoying for certain tools, right? But on the other hand, then you still have this local linearity, right? Which is very nice and very convenient for other, for other tools. So yes, we do have, in fact, I cut all these slides out, but no, sorry, it's not here. But yes, for instance, the limit cycle that emerges from a cycle in the graph, that one can be understood with a hop bifurcation, even though the hop bifurcation theorem doesn't apply. It doesn't apply because locally your system is linear, so you don't predict that you get a limit cycle when your fixed point goes from stable to unstable. But that's when the limit cycle emerges. Even though the limit cycle is cutting through different hyperplanes and so on, it's emerging at the same time, right? So again, it's with the bifurcation theory, like many of the theorems, of course, we can't just apply straight out of the box, but there's a spirit of them that we observe is very similar, and so there should be some way of adapting. Yeah.
First off, let us thank Professor Curto and Dr. de Guerriere for the very nice talk of this afternoon.